ESS Ecosystems and Ecology 1, Part 4 strengthens all of the concepts presented in movies Parts 1 to 3. In Part 4, I will focus on an analysis of production by working through different approaches to presenting production. Here's an outline of the Ecosystems and Ecology units. There are two distinct units, Ecosystems and Ecology 1, Ecosystems and Ecology 2. This movie is focused right here. Here are the three IB syllabus statements that drive all of movie Part 4. Define the terms and calculate the values of both gross primary productivity and net primary productivity from given data. Define the terms and calculate the values of gross secondary and net secondary productivity from given data. Calculate the efficiency of energy transfer from one trophic level to another. Let's start with a close analysis of calculating efficiency of energy transfer from one trophic level to another. Efficiency is best defined as output divided by input times 100 of the 10,000 joules per meter squared per year available to the primary consumers from the producers. The primary consumers only store at a rate of 1,000 joules per meter squared per year. So the input is 10,000 joules per meter squared per year, while the output, that's what's been transferred to the next trophic level, is 1,000 joules per meter squared per year. Thus the efficiency is 10%, 1,000 divided by 10,000. You can quickly see in this productivity pyramid that the efficiency of energy transfer from any one level to another is 10%. 10% is a general estimate of efficiency in energy transfer from one trophic level to another. Actual efficiency values will vary depending on the types of organisms involved. Here is a diagram displaying energy flow through a food chain. You can quickly see that the efficiency of energy transfer from the producers, NPP, to primary consumers, NSP, as 10%, because NPP is 8 times 10 to the third kilojoules per meter squared per year, while the NSP of consumers is 8 times 10 to the second kilojoules per meter squared per year. The output divided by the input times 100 would be 10%. Now, other efficiencies can be calculated. So, for example, of all the incoming solar radiation, some of which is reflected from clouds, the Earth's surface, off the surface of the plant itself, and some of which evaporates water, how much is transformed to the photosynthetic organic matter of the plant, in other words, GPP. The output is GPP, 1 times 10 to the fourth kilojoules per meter squared per year, divided by the input, which is the amount absorbed here at 0.5 times 10 to the sixth kilojoules per meter squared per year. The efficiency here is very low, at approximately 1%. Of all the incoming solar energy, not very much is transformed to the chemical energy by producers. Can you calculate the efficiency of GPP to NPP using the data here? If you do a bit of mental math, you might be able to see that it's a very high efficiency value. In fact, it's nearly 80%. Get your calculator out to confirm this value. So this slide asks you to calculate the energy efficiency in the transfer of energy from level to which level. Now let's do one together and let you practice some of these others on your own. What is the efficiency of energy transfer from the autotrophs, the producers, to the primary consumers? So 3368 kcals per meter squared per year. That's the output divided by the input, which is 20,810 kcals per meter squared per year, times 100. The efficiency is 16%. Here is the same productivity pyramid shown in the last slide. If you do some mental math, you can see the efficiency of energy transfer from primary consumer to secondary consumer is approximately 10%. What is the efficiency of energy transfer from secondary consumer to third level consumer? 21 kilojoules per meter squared per year divided by 383 kilojoules per meter squared per year times 100 gives a result of 5.5%. You can check the math on your own to confirm your understanding of calculating efficiency. In this slide, you can see NPP values for various biomes in grams per meter square per year. Keep in mind that productivity values can be presented in mass or energy terms as rates. You should already know that the limited length of food chains at 4 or 5 trophic levels is mostly determined by the transfer of low-quality heat out of the system with every trophic level. But a system with a greater net primary production, such as a rainforest biome, might be able to support a slightly longer food chain than a system where the NPP was less. Food chains are limited to 4, maybe 5 trophic levels, simply because energy has been transformed to a less usable, less ordered form, known as heat, and this is due to the second law of thermodynamics. As well, productivity, more or less, at the producer level could influence the length of food chains. In other words, if there's a lot of productivity, as would be found in a tropical rainforest biome, possibly the length of the food chains could be longer. Thirdly, the efficiency values between levels could influence the length of food chains. In other words, if the efficiency is high from one trophic level to another, then possibly the length of the food chain could be longer. And the top trophic levels, the top carnivores, are vulnerable simply because they tend to be rare. They're low in number, such that random catastrophic events would be more likely to impact the population. Their genetic diversity is less, and this can have negative consequences for the population. And as a result of their rarity, they're more valuable, thus of higher interest to poachers. As well, top carnivores are dependent on the success of 2 or 3 trophic levels below them, so any negative impact on any of the trophic levels below would negatively impact the carnivores as well. And lastly, non-degradable toxins accumulate or magnify in the tissues of top carnivores. So as you consider the lengths of food chains, efficiencies, and the impact of people, let's briefly compare the terrestrial and aquatic food chain. First, aquatic systems, this one, begin with a lower efficiency of solar energy to chemical energy because of greater loss of solar energy due to reflection from the surface of the water. As well, producers at depth will receive less solar energy due to the absorption of light by the water. So the NPP of aquatic systems is less than the NPP of terrestrial systems. Now, NPP will vary biome to biome, and a greater NPP could support longer food chains. Thus, the terrestrial food chain could be longer as a result of higher NPP at the base. A last aspect of energy efficiency has to do with choices that humans make about what they eat. In terrestrial food chains, humans tend to eat low, plants and or primary consumers such as cattle, chicken, or pigs. In aquatic food chains, humans tend to eat high. Humans appear to prefer eating tuna as compared to plankton. As such, the efficiency of energy use in the aquatic chain is low. So with this slide, I'll review some of the calculations involved in the flow of energy and matter through food webs. I will move along relatively quickly with minimal review of the equations, and I'll be talking through the calculations. Take notes as need be, stop the movie as need be. See me in class if you have questions. Given the information in this energy flow diagram, can you calculate GPP? Incident solar radiation is 1,880 times 10 to the 6th kilojoules per meter square per year. 1,856 times 10 to the 6th kilojoules per meter square per year is either reflected or used to evaporate water. And the difference between this value and this value is GPP, which is 24 times 10 to the 6th kilojoules per meter square per year. Notice that NPP, by the way, is given here. It's the energy available after respiratory losses, energy available to the next trophic level up. The calculation of the NSP of the seed-eating birds goes as follows. We subtract the quantity of respiration and feces from the quantity of food ingested by the birds, and we get a value of 0.8 times 10 to the 3rd kilojoules per meter square per year. Now, we might be able to calculate the GSP of the seed-eating birds, depending on how the information is provided in the diagram. In this case, because respiration and feces are bundled together in a single value, we cannot calculate GSP specifically. So the next question is to calculate the efficiency of energy transformation by the spider. Now this requires a couple of steps. First, determine the NSP of the spider. Easy mental math provides a value of 200 kilojoules per meter squared per year. 700 minus 500 gives us 200 for the NSP of the spider. Now, the output is 200 kilojoules per meter squared per year, while the input is 700 kilojoules per meter squared per year. We divide, multiply by 100, and we get a value of 29%. In other words, of all the energy taken up by the spider stores 29% of it at the value of 200 kilojoules per meter squared per year. So let's calculate the energy efficiency of energy transformation by the field mouse, which is here. The NSP of the field mouse, the output, is given here as 2,000 kilojoules per meter squared per year. The input is 116 times 10 to the third kilojoules per meter squared per year. You divide, multiply by 100, and you get a value of 2%. Of all the energy taken up by the field mouse, it stores only 2%. Now, the large difference in energy efficiency between the spider and the field mouse can be explained by differences in their respective levels of activity. The field mouse is a warm-blooded creature as well, maintains a high body temperature, and spends a lot of its food energy to maintain that high body temperature. Energy is spent in being warm-blooded, and that lowers the efficiency of energy use in the field mouse. So with this data table, I've asked two questions. Calculate the NPP of the alfalfa field, that would be this value, and calculate the autotrophic respiration of the rainforest, this value. You should remember that GPP minus respiration gives us NPP, so this value, number 1, is 15,200 kcals per meter squared per year. We can rearrange the equation to calculate this. 45,000 minus what value gives us 13,000, and the answer is 32,000 kcals per meter square per year. Here is the complete table, but I wanted to come back to this table to make the point that NPP is dependent on GPP and autotrophic respiration. The autotrophic respiration in the rainforest is very high simply because plants in the rainforest, big trees with all of their trunk and large quantities of root, have very high levels of respiration. The low levels of autotrophic respiration on the alfalfa field is because alfalfa is a small annual plant with small roots and no trunk, so the alfalfa has a high ratio of photosynthetic tissue compared to respiratory tissue, so its NPP is relatively high. Now notice that the net community production in rainforests is nearly zero, and that's because heterotrophic respiration is very, very high. Consider all the animals of the rainforest, particularly insects. In the alfalfa field, people lower the heterotrophic respiration by using insecticides, killing all the insects. People erect fences, keeping out many of the herbivores. As a result, the net community productivity on the alfalfa field is high. And this is what agriculture is all about. Let's look at secondary production more closely. Hopefully this slide looks familiar to you. Food eaten minus feces is gross secondary production, this flow right here. GSP is the energy assimilated by the heterotroph. It's the energy available for use by the animal. Now, net secondary production is the rate of energy storage after respiratory losses. It's the new mass on the animal. The new mass is the energy available to the next trophic level up, including people. The new mass is potentially the sustainable yield for a farming situation involving animals. GSP is food eaten minus feces, or GSP is A, the energy assimilated into the body of the animal. NSP is A minus R, in other words, NSP is P. Remember, all of the flows in this diagram would be measured as rates. Let me run through each of the questions that I've asked here. You can stop the movie now and practice on your own. I'll start with question 1, identifying each flow as a process. 1 is feeding, 2 is assimilation, or GSP, 3 is feces, 4 is respiration, and 5 is NSP, new mass of the animal. GSP is 1 minus 3, or this flow, 2. NSP is 2 minus 4, or 5, as new mass. If the animal as a system is in equilibrium, the inputs and outputs would be equal. In more specific terms, listen carefully, 2 and 4 would be equal values. Thus, NSP, shown here as 5, would be 0. Based on the values here, given in black, GSP, number 2, would be 50 grams per year. NSP, number 5, would be 10 grams per year. This is a graph showing the steady-state equilibrium of a cattle farm over a period of many years. There's a growth in the herd of the cattle, then a harvest, a growth, and a harvest, and the system is maintained at equilibrium over many years. The NSP of the system would be 40 times 10 to the 6th minus 30 times 10 to the 6th. That's this harvest, if you will. The NSP is 10 times 10 to the 6th kilograms per year. The sustainable yield for the farmer is exactly that, 10 times 10 to the 6th kilograms per year. I'll answer these questions here with this diagram. GSP is F minus W, or A. NSP is A minus R, or P. The input, GSP, is greater than the output, R, so that the animal grows from year 1 to year 2, as can be seen in this diagram. In other words, NSP is positive. The mass change from year 1 to year 2, calculated by subtracting the mass at year 1 from the mass at year 2, is NSP. In the last slide, you were looking at a single organism, and I asked questions about GSP and NSP, but the same questions could be asked of a population, group of individuals of the same species living in a defined area. The system, represented as a box, is the entire population. Think of a fish population, and that fish population would be here in year 1. Food is an input, feces is an output, respiration is an output, and any fish death or mortality would also be an output, and the population grows from year 1 to year 2. So NSP is the growth in the population over the year. NSP is the difference in mass of the population from year 1 to year 2. The difference in mass is NSP, and it's also the sustainable yield if someone were farming this fish population on a yearly basis. So let's try our hand at a problem. Assume you started with 100 snails instead of 1 or 2, and the total mass of the 100 snails was 100 grams at the start, say year 1. For the purposes of this question, assume the snail population's total mass increased to 110 grams over 10 days. Now let's view the snails as a natural resource and imagine that you're a farmer of snails and that you sold snail meat to a restaurant every 10 days. What is the NSP for the farmer in this scenario? Provide units. Well, the snail population, which is the resource, starts at 100 grams and grows to 110 grams over 10 days. So 110 minus 100 means that the NSP is 10 grams per 10 days. If you maintain the snail farm in equilibrium, what is the sustainable yield? Be specific. It is 10 grams over 10 days. I've come back to this diagram and asked the question, calculate the NSP of the grasshoppers, and the question appears challenging because I've blocked off the value of respiration and feces, and I've given you the value of the ingested food, but how do you calculate net secondary production without respiration and feces? Well, remember that net production is the energy available to the next trophic level up, so the NSP of the grasshoppers is 700, that goes to the spiders, plus 69 times 10 to the third, that goes to the decomposers. If we add 69 times 10 to the third and 700, we get 69,700 kilojoules per meter square per year as the NSP of the grasshoppers. As a model, what we have here is a diagram that helps us understand complicated systems by simplifying them. But the model is limited. Are these the only 3 primary consumers in the system? Does all of the NSP of the grasshoppers go to the spider? Is the spider the only secondary consumer in the ecosystem? Let me answer the questions that I've asked here without any explanation, See me in class if you're not sure. GPP is B minus C, or GPP is E plus F plus D, because E and F together would be NPP, and NPP plus respiration would equal GPP. Now, NPP is B minus C minus D, or, as I've earlier stated, NPP is also E plus F, the amount of energy available to the next trophic level up. The GSP for the herbivores is E, while the NSP for the herbivores is E minus G. In this slide, you're shown a food chain and values for energy flows are given, and I've asked to calculate W, X, Y, and Z. W, seen here, would be 8,000. 40,000 minus 32 would give us a value of 8. X, seen here, would be 7,600, be 8,000 minus 400 to give us 7,600 for respiration. Y, seen here, would be 80. 400 minus 320 gives us 80. And Z would be 68. 80 minus 12 would be 68 for respiration. The efficiency of net production from herbivores to carnivores is determined by taking the net secondary production of the carnivores and dividing it by the net secondary production of the herbivores. So 12 divided by 400 times 100 gives us an efficiency value of 3%. Units are not provided by the diagram, and the units, if provided, should be rates. With this last slide of the movie, I'll answer these two questions. Write an equation that represents the first law of thermodynamics. The first law is a law of energy conservation, so inputs and outputs, regardless of energy form, will be equal. Thus, C is equal to F plus U plus P plus R. GSP is C minus F, or A is GSP. NSP is C minus F minus R, or P is NSP. NSP is also A minus R. For future reference, the energy lost in urine production will be ignored. And that brings an end to IB ESS Ecosystems and Ecology 1, Part 4.